Okay, so we want to do this example. We have this cylinder of radius 2 along the z-axis going from z is equal to 1 to 4. We have a vector field, and we want to compute the surface integral of the curl of f over this surface. Okay, so we want to use Stokes Theorem. We want to compute this as a line integral around the boundary. But this is going to take a little work, again, with the orientation. So this is the x-axis, this is the y-axis, this is the z-axis. So we want this cylinder roughly like this. Again, this is not to scale, and I know I'm not drawing this very well. Okay, so whoops. Okay, maybe I can do a better job like this. Okay, but this is a cylinder that is going around the z-axis. Okay, like this. Doesn't look like a cylinder, but trust me, it is. So this would be like z is equal to 1, and this is z is equal to 4, and we want the outward pointing orientation. So let me, so the boundary, so there's a couple of things. We have to figure out what the boundary curve is, or r in this case, and then we have to figure out what the orientation. So there's two boundary curves. There's this top boundary curve. This is circle of radius 2 in the z equals 4 plane, and there's the bottom boundary curve that is the circle of radius 2 in the z is equal to 1 plane. Okay, so how can we figure out whether to put the counterclockwise or clockwise orientation on these curves? So the cylinder has outward orientation. So one way to think about this, so Dr. Yaskin has a very good illustration of this in his book. I'm going to try to say it here. So take some point on the surface of the cylinder here. Let me do this in different colors. Okay, now imagine the normal vector. It's pointing out of the screen. And if you were to draw a circle around this curve, and you wanted this circle to have the same orientation as the surface, would it have the counterclockwise or clockwise? Well, by the things we've been talking about, it would have the counterclockwise orientation. If you think about this as enclosing the region that enclosed this dot, then if you walk around this circle with your left arm sticking out, it's going to be sticking over that region if you walk in the counterclockwise direction. Now, as you move this circle up to the purple line, notice that this line, so this arrow, as it rotates up here, is going to be going in that direction, okay? And so that means you want the arrow on the purple circle to match with that arrow. So you want it to be going in that direction. Okay, so the top of the boundary is going to have the clockwise orientation. If you do something similar, if you take this point and move it down, if this arrow comes down around to the bottom of the circle, it's going to be pointing to the right. And if you move down to the bottom boundary curve, you want also the arrow to be pointing to the right there. So that's going to have the counterclockwise orientation. So you have two boundary curves. The top boundary curve has the clockwise orientation, and the bottom boundary curve has the counterclockwise orientation. Okay, so then to use Stokes' theorem, we're going to have to split the line integral up into two pieces, the top circle and the bottom circle. Okay, so let's do the top circle first. So a parameterization for the top circle is r of t is equal to 2 cosine t, 2 sine t, 4. Okay, I actually need to say something here. This is the counterclockwise parameterization. I needed the clockwise parameterization, but I fixed this after I compute the integral, but I wanted to mention something now so that you are not confused. Now we will get back to where I was. And r prime of t is equal to minus 2 sine t, 2 cosine t, 0. Okay, so now when we compute the line integral, this is going to be the integral t equals 0 to 2 pi. This is f, so in the parameterization, x is 2 cosine t, y is 2 sine t, z is 4. So this is going to become, I'm just going to factor out the 1/4. So this is 1/4, y is 2 sine t, x is 2 cosine t, and then x plus y is cosine t plus sine t. And then remember, we dot this with r prime. So we're going to dot this with minus 2 sine t, 2 cosine t, 0. Okay, and then so we're going to do this integral, dt. But notice that we've got some good trig stuff to help us. So 2 sine t times minus 2 sine t, that's minus 4 sine squared, minus 2 cosine t times 2 cosine t, that's minus 4 cosine squared. So this is going to be equal to the integral t equals 0 to 2 pi, and then the 4 cancels with the 1/4, so this is minus 1 dt, or this is equal to minus 2 pi. Okay, so now let's think about what we've just done. We've just computed the line integral of f around the top boundary curve, but what is the orientation of that curve, of that parameterization? Notice that goes counterclockwise. Okay, so when we go in the counterclockwise orientation, we get minus 2 pi. But we want the clockwise orientation, so then what does it mean? It means that the line integral, so we can write it like this, if we call the top curve C1, the line integral around C, and I'm going to draw the arrow that way, meaning counterclockwise or clockwise orientation of f dotted with ds, this is going to be equal to 2 pi. This is equal to 2 pi. Okay, and now we need to find what the line integral of f is on the blue boundary. Well, this is going to be counterclockwise, so we can say r of t is equal to 2 cosine t, 2 sine t, and here z is equal to 1. This is the counterclockwise parameterization, and so the line integral is going to be the integral t equals 0 to 2 pi. Now the vector field y over z, y is 2 sine t, z is 1. This is 2 sine t minus x is 2 cosine t minus 2 cosine t. X plus y is 2 cosine t plus 2 sine t. And then if this is r of t, r prime is minus 2 sine t. Sorry, that's a 2 there. R prime is minus 2 sine t, 2 cosine. So this is dotted minus 2 sine t, 2 cosine t, and then 0 dt. Let me zoom out a little bit. And again, we're going to have some good trig stuff help us. This is the integral t equals 0 to 2 pi, and it's going to end up being minus 4. And this is equal to minus 8 pi. So all in all, we have minus 8 pi from the blue integral, 2 pi from the purple integral. So the overall answer is going to be minus 6 pi. So let me write that. This is the overall answer. Okay, but remember, the difficult part here was coming up with what the orientation should be.